Assistant Professor in the Department of Electronics and Communication, DMS College of Engineering. I welcome you all to the course Elements of Electronics Engineering. The first unit of this course is Semiconductor Diode and its applications. So here we can see the pictorial representation of diode and also how it is represented symbolically. Here you can see the special type of diode, which is Zener diode, how it looks. And here we can see the regulated power supply, which is one of the major applications of diode. Before starting this unit, you need to know what are the prerequisites for this unit, for understanding the concepts of this unit. So the prerequisite for this unit is semiconductor theory. So I will brush the important points which are essential to understand the concepts of this unit. What is semiconductor? We all know materials are of three types: conductors, insulators and semiconductors. Conductors are materials which easily allow the flow of current. Insulators are materials which restricts the flow of current. And what is semiconductor? Semiconductor is a material which has conductivity between that of a conductor and an insulator. We all know the popular examples for semiconductor are silicon and germanium. Why do we need semiconductor? Semiconductor is needed in order to have control over the current. That's why we need semiconductors. As I mentioned before, the examples of semiconductors are silicon and germanium. These are tetravalent atoms. Tetravalent meaning there are 4 electrons in the outermost orbit, and they form a structure or a crystal by the means of covalent bond. That is, a silicon atom is attached to the neighboring silicon atoms by the means of covalent bond, which is nothing but sharing of electrons. There are 2 types of semiconductors: intrinsic and extrinsic. Intrinsic meaning pure form of semiconductor. That is, a pure silicon crystal or a germanium crystal are examples for intrinsic semiconductor. What is extrinsic? Extrinsic is when we add impurities to the pure form of semiconductor. The process of adding impurities is called as doping. We add impurities in order to enhance the conductivity of the material. The extrinsic semiconductor is again divided into 2 types: p-type material and n-type material. What is p-type? P meaning positive. It has majority charge carriers as holes. Holes are positive charge carriers. Holes are nothing but absence of electron. How is a p-type semiconductor formed? When we add trivalent atoms into a pure semiconductor, we get p-type of material. Trivalent meaning the atoms which have 3 valence electrons or 3 electrons in the outermost orbit. So examples for this trivalent atoms, meaning you have examples have boron. So these are trivalent atoms. And what is n-type semiconductor? N means negative. So n-type have majority charge carriers as electrons, which are negative charge carriers, and minority charge carriers as holes. How is n-type semiconductor formed? When pentavalent type of atoms are added into a pure semiconductor, we get n-type material. What are the examples of pentavalent atoms? Phosphorus, arsenic, antimony, etc. So these are examples of pentavalent atoms. So the main point to remember is we get p-type material when we add trivalent atoms, and we get n-type semiconductor when we add pentavalent atoms. A p-type semiconductor has majority charge carriers, that is more in number. Majority charge carriers as holes and minority charge carriers as electrons. Whereas in the n-type, which is formed by doping pentavalent atoms, has majority charge carriers as electrons and minority charge carriers as holes. So knowing these major points as the prerequisite for this unit, let's jump into the objective of this unit. So through the study of this unit, you will be able to learn the working of two-terminal semiconductor device, which is diode, and how the circuits work which have diodes in it. We also be lastly looking into one major application of diode, which is regulated power supply. The main advantage of using diodes is as a rectifier, which is used to convert AC into DC. AC means alternating current and DC means direct current. So we all know and we all use appliances and equipments in our daily life like mobile phones, TV remotes, portable MP3 players, computers. All these work on DC, or they run on DC, that is direct current. And what we are getting from the power outlets at our places is AC, which is alternating current. In order for all these equipments to work, we need DC, but then we have AC. So it's essential to convert AC into DC. This can be done by using diodes. Under this unit, we will be studying these topics. The first topic is how does a diode work? The working principle of the diode. And the characteristics of the diode, in the sense, how is the current and voltage of a diode related? How can this characteristic be mathematically represented by an equation, which is Shockley's equation? We'll also be looking into parameters and specifications of diode. Every manufacturer who manufactures diode will specify the values of different specifications and parameters of diode, so that we as a user get to know what are the parameters and specifications for the safe use of diode in a circuit. Later, we'll look into two types of rectifiers. As I told, rectifier is a circuit which converts AC into DC. There are two kinds of rectifiers we are going to study in this unit. First one is half wave rectifier and the next one is bridge wave rectifier or bridge rectifier. So we are going to study different parameters and we are going to derive the efficiency of half wave rectifier and bridge rectifier. Later, we are also looking into what happens if a capacitor filter is used after the half wave rectifier or after the bridge rectifier. What is the effect of using a shunt capacitor filter? We'll also look into one special type of diode which is called Zener diode. Zener diode is basically used for voltage regulation, and we'll also be looking into the characteristics of Zener diode. Lastly, as I told, we'll be looking into one major application of diode, which is regulated power supply. Now, what is a semiconductor diode? Semiconductor diode is a two-terminal semiconductor device which is unilateral. It allows the flow of current in only one direction and opposes the flow of current in opposite direction. The two terminals of the diode are anode and cathode. You can see the symbolic representation of diode over there. We have represented that by a triangle and later on a line. It's basically a representation of an arrow which says how the current flows in a diode. The current is flowing from anode to cathode. This is how a diode is symbolically represented. Now, diode offers less resistance and allows the flow of current from anode to cathode. It offers very high resistance or restricts or opposes the flow of current from cathode to anode, which is opposite. It can be biased in two ways. What is the meaning of biasing? Biasing is applying voltage across the terminals of the diode. We have two types of biasing. One is forward bias, the other one is reverse bias. Now, diode is also called as a PN junction. It conducts or allows the flow of current when it is forward biased. It opposes the flow of current when it is reverse biased. Now, this indicates, the symbol indicates the current is allowed in this direction from anode to cathode, whereas the current flow in the opposite direction is opposed or restricted. That's why diode is called as a unilateral device. Unilateral means the diode allows the flow of current only in one direction. It opposes the flow of current in the opposite direction. The main point to remember or take away from this slide is that the current flows from anode to cathode, and the opposite way of current flow is not allowed. We look into first what is an unbiased diode. I told initially biasing means applying voltage across the terminals of a diode. That is called biasing. What is the meaning of unbiased diode? A diode which is simply lying on the table where we have not applied any voltage, that is called as unbiased. We are not applying any voltage across the diode at all. That is meaning of unbiased diode. What happens in an unbiased diode? Before that, we need to know how is a diode constructed. Diode is nothing but a PN junction. Diode is nothing but a PN junction. What we do is, we take a pure form of semiconductor, which is intrinsic semiconductor, a silicon crystal or a germanium crystal. On one side, we dope the trivalent impurities. That forms the N region. That forms the P region. And on the other side, we dope pentavalent atoms, which forms the N region. I repeat, we take an intrinsic type of semiconductor, which is a pure form of silicon crystal or a germanium crystal. On one side, we dope the trivalent atoms, which form the P type of semiconductor. On the other side, we dope the pentavalent atoms, which form the N type of semiconductor. And in between, what we have is the junction. This is the P side and this is the N side. And on either side, we provide the metal contacts and terminals. So the terminal which is attached to the P side or P type of semiconductor is called as anode, and the terminal which is attached to the N type of semiconductor is called as a cathode. We all know in the P type, the majority charge carriers are holes, which are positive charge carriers, and minority charge carriers are electrons. Whereas on the N side, majority charge carriers are electrons and minority charge carriers are holes. So when we have an uneven distribution of charge carriers, the tendency is that in order to establish equilibrium, the tendency is that the charge carriers move from higher concentration region to lower concentration region. So here on the N side we have more electrons. Here on the P side we have less electrons. Whereas on the P side we have more holes, and on the N side we have less holes. So in order to balance or to get equilibrium, the normal tendency is that the charge carriers which are more in number here, electrons, try to move from n type to p type, and similarly the holes which are majority here and minority there will try to move from p side to n side. This exchange of charge carriers or movement of the charge carriers across the junction is called as diffusion. This is called diffusion. So what happens here is the electrons which are majority in number here tries to move from n side to p side. Once the atoms here lose the electrons which are negative charge carriers, they become immobile positive ions, whereas the holes which are majority here and minority here, they are moving from p side to n side. The atoms here are losing the holes, so they are losing positive charge carriers. They become negative ions. This happens majorly near the junction. So what happens in the junction is that a layer of positive ions is formed on the n side since it loses electrons, and a layer of negative ions are formed on the p side because it is gaining electrons. This region where we have immobile positive ions and negative ions and it is totally depleted of any free charge carriers is called as a depletion region. This is called as a depletion region, which is depleted of any charge carriers. But still, we can see here that the number of electrons here is still more and number of electrons here is still less. So the tendency to establish equilibrium is that electrons still try to move from n side to p side and holes still try to move from p side to n side in order to establish equilibrium. But because of the formation of the depletion region, it is not possible because depletion region acts as a barrier. It acts as a barrier. It restricts the further movement of charge carriers from n to p side or p to n side. So this depletion region acts as a barrier. The potential here existing in the depletion region is called as barrier potential or junction potential or built-in voltage or cut-in potential or cut-in voltage. There are different names given to the potential or the barrier which is existing at the junction. What are the names given to this potential, which is the barrier, is called as a barrier potential or junction potential or built-in potential or cut-in potential. So since you have a barrier here, there is no further movement of electrons from n side to p side or holes from p side to n side. So the net current is zero because there is no movement of charge carriers. The meaning is, if you are not applying any biasing or not applying any voltage to the diode, then there is no current flowing. Net current is zero. Next we'll move on to what is a forward bias diode. When you have a diode here like this, if I apply P type, if I connect P type to positive of the battery and N type to negative of the battery, if you do this, this is called forward biasing. P to positive, N to negative. If you are applying potential in this way, this is called forward biasing. What happens in forward biasing? We can see negative of the battery is connected to N type. What is more in N type? Electrons, which are majority charge carriers. Electrons are negative charge carriers. What happens to negative and negative? We know that negative repels, right? So the electrons move from this side N type to P type provided we have a barrier here, right? The applied potential is greater than the barrier. If the applied potential is greater than the barrier, then the electrons move from N side to P side and back to the battery. Similarly, you have positive applied to the P side. What is more in the P side? Holes, which are positive charge carriers. This is also positive and you have applied positive potential. So positive repels. Suppose the applied voltage is greater than the barrier, Then the holes also try to cross the junction from P side to N side and back to the battery. So how is the movement of charge carriers? So electrons move from this side and it crosses the junction, provided this potential is greater than the barrier, then it crosses the junction, then it flows back to the battery. Whereas, how is the holes moving? Holes move from positive, it is repelled here, the holes here cross the junction because you have applied a greater potential here than the barrier, then it moves back to the battery. In this way we have a current flow. The flow of holes is from positive of the battery to the negative of the battery, whereas the electrons are moving from negative of the battery to the positive of the battery. So how is the conventional direction of current flowing? We all know from the basics that the conventional direction of current is always same as the direction of flow of holes and opposite to the direction of flow of electrons. So the conventional direction of current is from anode to cathode. This is anode, this is cathode. How are the holes flowing? From positive of the battery, from P side to N side and back to the battery. So this is how is the conventional direction of current. Since the current here is because of majority charge carriers which are more in number, the current will also be more, and the current which is flowing in a forward bias diode is called as a forward current. Now we all know that there is a barrier here existing because of the depletion region. What is the potential which is existing here? What is a barrier? So in a silicon diode, the barrier potential is 0.7 volt. For a germanium diode, the barrier potential is 0.3 volt. So we very well know that for a current to be flown in a diode, to make the current flow in a diode, then we need to apply a potential greater than the barrier potential. So knowing this basics, let's move on. I'll just show you an illustration of how a forward bias diode works. So here is a video where we have a battery connected, and then we have a diode, and this is a current limiting resistor. Here you can see that if I apply a voltage which is less than the barrier potential, the diode I have chosen here is a silicon diode. We know that the barrier potential is 0.7 volt. Suppose the applied potential is less than the barrier voltage, there will not be any current flow. Assume these are all the charge carriers. The movement of the charge carriers indicate the flow of current, right? So it all depends on what voltage I am applying here. The applied voltage should be greater than the barrier voltage. Now I'll edit the voltage, which is 200 milli, which is not sufficient for the diode to conduct, to 5 volts. So now you can see the current is flowing, right? So here the green line indicates the potential. How is the potential there here and the potential here? The potential here is less, right? It is connected to diode. The potential here is more. What is the potential that we applied? 5 volt. And the moment of the charge carriers indicate the current flow. Now, what is a reverse bias diode? How it works? Now we saw in a forward bias diode that there is a current flow from anode to cathode. What is the meaning of reverse biasing a diode? Connecting P type to negative and N type to positive. This is the opposite way that we did for forward biasing. So if P is connected to negative and N is connected to positive, this is called as reverse biasing. What happens in a reverse bias diode is that the N type, which has majority charge carriers as electrons, are attracted towards the positive of the battery, and in the P type, where we have majority charge carriers as holes, which are positive charge carriers, get attracted to the negative of the battery. So basically what is happening here is the electrons move in this way and the holes, which are positive charge carrier, they are attracted towards the negative and they move in this way. So what is happening to the majority charge carriers? They are not crossing the junction. They are moving away from the junction. So there is no current flow because of majority charge carriers. And moreover, what happens to the depletion region is that since the electrons are moving away from the junction and the holes are moving away from the junction, the depletion region widens. Unless in case of forward bias diode, the depletion region narrows. But here the barrier or the depletion region widens because the charge carriers are moving away from the junction. Then what happens is that because of this barrier here and the potential which is applied here, the minority charge carrier flow is supported. How? Because the minority charge carriers are holes here and minority charge carriers are electrons here. Electrons are negative charge carriers, right? They are attracted towards the positive. Where we have applied positive here and we have positive here as well because of the barrier. So though this barrier is restricting the flow of majority charge carriers, they aid or help the flow of minority charge carriers. So the electrons which are minority here will cross the junction and the holes which are minority here cross the junction. Since they are minority, where they are very small in number, though they flow, the current due to it will be very, very less. This is called as reverse current. There is a very small reverse current flowing in a diode. What we initially defined that the diode, when it is reverse biased, it does not allow the flow of current, right? It is not allowing the flow of current due to majority charge carriers, but there is still a very small current flowing because of minority charge carriers. For a silicon diode, the reverse saturation current, what we call the reverse current, is in the order of nanoamperes. For a germanium diode, it's in the range of microamperes. Microamperes meaning 10 to the power of -6 and nanoamperes meaning 10 to the power of -9. Such a small current will be flowing. That small current which is flowing in a reverse bias diode is called as reverse saturation current. If you keep on increasing this voltage, the reverse current won't change. The reverse current is dependent on temperature. The temperature, if it increases by 10 degrees centigrade, then the reverse current doubles. So this current is almost constant up to certain limit of the reverse bias voltage. Okay, so this very small constant current which is flowing in a reverse bias diode is called as a reverse saturation current. Potential or a battery applied, and there is a diode. You can see that this is anode and this is cathode, and you have a current limiting resistor. We have a ground connection. So what has happened here, positive is the longer one in the battery. Okay, the positive of the battery is given to cathode, which is N type, and the negative is given to the P type. What type of biasing it is? Reverse biasing. In a reverse bias diode, the current does not flow, okay, or it is very minimal because of the minority charge carriers. I'll run this video. What I'll be doing through this video is that I will change the battery voltage. I'll edit now it is 2 volts plus 2 volts. What if I change it to -2 volts? That means it's as good as reversing this. Then instead of reverse biasing, it will become forward biasing and there is a current flow, right? Now if I make it -5, even greater than it, so you have a current flow. I've made this potential negative so that instead of reverse biasing, it has become forward biased. Now if I again apply a positive voltage here, you can see the current stops because the diode is reverse biased. It does not flow, it does not allow the flow of current. Now we'll move on to the characteristics of a diode. What is the characteristics of a diode? It is a plot of current through the diode and voltage across the diode. So if you're plotting I versus V, this is called as characteristic of a diode. Now what you can see here is in the first quadrant we have a characteristic, and in the third quadrant we also have a characteristic. In the first quadrant, this describes how a forward bias diode behaves. So we know how a forward bias diode behaves. we can see here near the 0, we have the current also as 0. Until the barrier potential is exceeded, this is the barrier potential or the cut-in voltage or built-in voltage, we have different names, right? Before the barrier potential, the current is almost 0. You can see here the current is almost 0. Once the applied voltage exceeds the barrier voltage, then only you have charge carriers moving across the junction and there will be a current flow, right? Once you exceed the barrier potential, or we also call as a knee voltage here, once you exceed that, you can see that the current increases exponentially. This is how a forward bias diode behaves. Now what happens in a reverse bias diode? We know that in a reverse bias diode, ideally there should not be any current flow because it opposes the flow of current. But still, we know that there is a small amount of current flow because of minority charge carriers. The small amount of current, which is almost constant when the voltage is increased in the negative direction, is called as the reverse saturation current. This is a very small current. This is the reverse saturation current. This current is almost constant until a voltage called as a breakdown voltage. This current is reverse saturation current. It is small because of minority charge carriers. I told it will be in the range of nanoamperes or microamperes. So this current is almost constant, but when you keep on increasing the reverse voltage, there will be a certain voltage point which is known as the reverse breakdown voltage. This voltage, if you exceed, then the current increases rapidly. It heats up the diode and the diode gets damaged. So this is a region that you have to avoid. Now every manufacturer who gives the diode will give what is known as a data sheet where he specifies what is the reverse breakdown voltage of a diode. Knowing that, you should make sure that in your circuit that you don't exceed the reverse voltage above the breakdown voltage, because if the diode breaks down, it gets damaged because of overheating, right? So these regions are the safe regions of the diode. This is when you forward bias, you get this kind of characteristic, and when you reverse bias, you get this kind of characteristic. So that's the explanation given here as well. We can just recap. Here is the first quadrant, which indicates the behavior of a forward bias diode. The current is nearly 0 when the forward voltage is below the knee voltage or the barrier voltage. Current is almost 0. And then as you exceed the forward voltage above the breakdown, above the barrier voltage, then the current increases exponentially. Whereas in the third quadrant, the characteristic represents the behavior of a reverse bias diode. In the reverse voltage is increased, the reverse current slightly increases, then on it becomes constant. This constant current is called as reverse saturation current. It's been given here, it's reverse saturation current. At the breakdown voltage, we have the diode breakdown. Because the current increases rapidly, it results in overheating of the diode and the diode gets damaged. So this region needs to be avoided. The mathematical equation which represents this characteristic. So now we have this characteristic, right? How to mathematically represent this particular curve is by what is known as the diode current equation, which relates the current through the diode and voltage across the diode. So how are these two related? This is called as a diode current equation, or which is also known as the Shockley's equation. So here we have the characteristic, here we have the mathematical representation for it. So it is I which is current flowing through the diode is equal to I naught. I naught is the reverse saturation current, which is the constant current here that you are seeing, that is I naught. I naught into e power exponential of Vd divided by eta into Vt minus 1 ampere. this is the unit. Okay, so here why we have exponential, because you can see here when you make this voltage forward bias Vd as more, what happens to the exponential term? It becomes more. So then we have an exponential increase in the current, right? So that is indicated by this term. We'll see what is the meaning of each of the terms here. Okay, so as I told, I naught is the reverse saturation current. That's the least current or the minimum current which is flowing in a reverse bias diode. That is reverse saturation current. And what is Vd? That's the voltage across the diode. So if you have a diode, what is the voltage applied across it? So that is Vd. Okay, so what is eta? Eta is called as an ideality factor. So what is this? How good the characteristic is resembling the ideal diode characteristic. So it is a constant, it does not have any unit. It is 1 for a germanium diode. If you are taking a germanium diode, then you have to take eta as 1, and 2 if it is a silicon diode. So eta is nothing but the ideality factor. And what is Vt? Vt is nothing but the thermal equivalent voltage. It is a voltage which depends on temperature. The definition of this thermal equivalent voltage or Vt is, it is given by Kt by Q. Okay, so K meaning Boltzmann's constant. We know this value from the basic physics. We know it is 1.38 into 10 to the power of minus 23 joule per degree Kelvin. So that's the unit. And T is the temperature, ambient temperature in degree Kelvin. Suppose it is in centigrade, then you have to convert it into Kelvin. So T is temperature in Kelvin. Okay, and Q is charge on an electron. So charge on an electron is 1.602 into 10 to the power of minus 19 coulomb. Okay, so suppose I assume the ambient temperature T as 27 degrees centigrade. So how do you convert the centigrade into Kelvin? You have to just add 273. So if you add 273 to 27, it results in 300. Now if I substitute all these values in the formula, you get 1.38 into 10 to the power of minus 23 into 300 divided by 1.602 into 10 to the power of minus 19. If you solve all this, we get the value of thermal equivalent voltage as 26 millivolt. So the value here is 26 millivolt. So this equation represents mathematically the IV characteristic of a diode.